and finish talking about, oh, it's in the other folder. There we are. Okay, so we just really scratched the surface on this. I just want to remind you that these Boltzmann diagrams will be on the test in some way. I will let you try to. I like to have you explain things in words because actually I was just talking to a friend of mine who works for Google, and he was like, you know, we need people who know the science, right? We don't need people who just know the science. We need people who can actually explain it. I would rather have someone who can explain the science than someone who's like the super PhD, because they have to explain it to your boss. And that's what these kind of explanations are good for. So we're explaining how these different diagrams, we talked about how to get this diagram. What does it mean, comes from where we got it from, and it even means something for natural history, is what we had, you know, and that is what ties the book together with everything else. We talked about how there are simple physical trends that determine binding energy that go from the size and ionization of the atoms, and that comes directly from the periodic table. So we have those different energies, and they follow predictable and universal trends that also shape natural history, because the difference between this energy and that energy determines how much it will be surrounded by water if it's exposed to water, as opposed to staying in the crystal. Okay? Now, the way that that really works out is, it's nice if we can understand that at a completely physics-based level, but we don't have to. We can measure the solubility just by putting it in a tube with some water and seeing how much of it dissolves. And that's an equilibrium between two phases. One is a solid, and the reactants the reactant is a solid, and the product is whatever ions there are, and of course they'll be up by whatever stoichiometric coefficient that it is. So as long as you keep this in mind, you can actually interpret a whole table like this. That's the one thing that you have to watch out for, though, is the fact if you're comparing manganese hydroxide to manganese sulfide, those actually have very similar numbers. But can you tell me why I shouldn't just say, oh, they're about as soluble as each other? Because their K values are very similar. Does that mean that they are as soluble? The percentage that stays in the solid phase, is that going to be the same? The K is the same, so at a first glance it would look like it could, but can anybody tell me the flaw in my reasoning? Or better yet, the flaw in my equation that I'm thinking of? What is the KSP? What is this for manganese, here we are, manganese 2 sulfide? It's going to go to ions, bracket Mn, bracket S, right? What's it going to be for that? Bracket Mn, bracket OH squared. So you're producing 2 negative ions for every positive ion, whereas here you're producing 1. And even worse than that, the OH is tied up with the water dissociation constant. And so if you really want to get into the whole thing about how pH interacts with solubility, with something like a hydroxide, you actually have to consider the kW of water. You have to consider a lot of other things. And honestly, like analytical chemistry really gets into that. But in this class, we're just kind of like, oh, just be aware of it, you know? Be able to do each calculation as needed, as is required in the homework. But even though Atkins doesn't give you too many KSP problems are actually simpler because there is no denominator. Remember that the solid, the activity of a solid is 1 by definition. A pure, in fact, you can think of it as activity is like concentration, right? And the activity of a pure solid that doesn't really have concentration, you know, it's kind of like we can set it to whatever we want because it doesn't have a concentration. It depends on how big of a chunk you have, but it doesn't depend on millimeters. Our equations don't depend on that. So our equations depend on concentration. The concentration of a pure substance is 1. 1 no units, by the way, not 1 molar. I want to be clear about that. Okay, but you can look up and down and you can see different things. Like, for example, aluminum hydroxide, even with accounting for the OH cubed, that is a really small number. Aluminum hydroxide is not very, hey.
Hi, visitors who are looking through your classroom upstairs.
Oh, okay.
I walked the line down.
Hello, welcome. Yeah. We have now, this is a small class, so we have now like 50% increased the size of the class, okay? But the other thing is, I'm recording these classes. These classes are kind of the last lecture before we go into a midterm test. And so actually the first part of this is going to be posted on YouTube eventually. But needless to say, if you're interested in seeing the first part, there it is. Okay, welcome. So we can say that aluminum, and remember that in the first couple chapters of A World from Dust, we talked about how aluminum is too sticky. Cadmium sulfide, okay, is sticky or not? Will it dissolve much or not? No, it's a big number, and you don't have to worry even considering the O3. In fact, you would say cadmium sulfide is actually more insoluble than aluminum hydroxide. So it's no good talking too much about cadmium chemistry in a sulfur-rich ocean. In fact, cadmium is only used by a couple of bacteria. Only now that we've gotten rid of sulfur do we actually have the cadmium chemistry being used in certain bacterial enzymes. Zinc sulfide. So you have this. You have zinc sulfide there as well. Zinc sulfide is also pretty insoluble. We're seeing a trend here. The sulfides are pretty insoluble when it comes down to it. Welcome. Hi. Just feel free to sit back and ask a question if you want to too. Okay. Iron hydroxide, medium soluble. Compare it to iron sulfide, and you have to do the calculation. You know, iron hydroxide with the third, though, that is more than twice the exponent when you're only adding a cube instead of a square for the OH. Iron hydroxide is more insoluble than iron 3 hydroxide, more insoluble than iron 2 hydroxide. So when you get to iron 3, it's going to drop out of the solution. And that was also in A World from Dust. This is how R.J.P. Williams made his predictions, by the way. He didn't have fancy data. He had KSPs, but he also had a bit of enough geology to be able to say, hey, these KSPs fit with what we see in general trends. So occasionally you'll find a paper that sort of says, oh, the general trend wasn't specifically followed here. And occasionally you can say that these were only general trends, but as far as the general trends go, he was spot on. Calcium carbonate, on the other hand, a very low number, a rather low number, and also that's in equilibrium with the CO2 concentrations. So there's complexities all over the place, but this is the kind of thing that somebody very smart, like R.J.P. Williams, could sit down with this table and make some kind of predictions about sulfur-rich chemistry versus oxygen-rich chemistry. And you can do these things. This is a thing, this is an example of a, this is too slow for us to do, but you can actually do stalactites. If you remember the beginning of chapter 4, talks about Camp Casey. Has anybody gone over to Camp Casey and you remember those dripstones that they have? You know, it comes from concrete, and it's a very common, we can reproduce that in the lab. Now, you might have noticed that I didn't get into too much detail about what exactly is going on. Because concrete is pretty complicated, I would have loved to say, here's a KSP, and that's the example. But that was probably good that it was too complicated to keep me from making it even more complicated. But you have the example of the different kinds of minerals that can be in concrete. They each have a KSP, and you can see that these log KSPs can be very big exponential numbers. So this is from this paper, and basically you can reduce concrete into being a bunch of calcium silicates, which are insoluble, and more soluble calcium hydroxide. And if you look on that, you can see that you can compare the KSPs and you can make predictions like that. Those dripstones form from the calcium hydroxide dissolving when the calcium silicates do not. And this is where you can get that data from, fun weekend reading, but I'm not going to ask you to do that. But the thing is, looking at those KSPs, you can actually look at the big thing. There's not too many counter ions available. There's really oxygen and sulfur. Nothing else makes a major counter ion except maybe carbonate. So you have sort of multiple things, and you see that there's a predictable difference between sulfide chemistries and oxygen chemistries. Now you have to account for the fact that oxygen usually doesn't bind as the oxide, it binds as the hydroxide, and water has that annoying Kw that complicates your calculations. But if you compare the log of the solubility product for each of these, you can see that if you follow the periodic table from left to right, you can see that there's this area over here where the hydroxide is the metal hydroxide. And I want to make sure I've got to follow this. The sulfide is the solid line, and the oxide is the dashed line. So here we have the KSPs of the sulfide. The sulfides are more soluble over here, less soluble over there, and the oxides follow the opposite trend. So over natural history, if you have a sulfur-rich environment early and a sulfur-poor environment, and a sulfur, like if you're going from having more sulfur to less sulfur, in an ocean with high amounts of sulfur, you're going to have these big numbers for the KSPs on the right side of the periodic table. So that means high amounts of sulfur will precipitate out the right side of the periodic table. And you really can do this by looking at the periodic table and dividing it into left and right. And the red circle is that the left side of the periodic table would precipitate more when oxygen increases. And so you have a balance between sulfur and oxygen, and you have, that goes with the availability. So as oxygen increases, these precipitate more, but these, the yellow circle, precipitates less and becomes more available. Again, cadmium enzymes are the natural extension that I didn't mention in The World from Dust. But the cadmium is a natural extension from this. You could have predicted this, that we would have some bacteria that are starting to use cadmium now that we have so much oxygen. But before it's useful, it's toxic. So you have all of these things going on. I want to point out that this is from R.J.P. Williams. He's comparing sulfides versus oxides, and he's using heats of formation. Right here, heats of formation, Chapter 1 calculation. He's going to the tables the same way that you're asked to do on the test, and he's bringing it out to the whole story of natural history. The good news is you get to look at his notes, because basically I'm transcribing his notes in the book. And so that's how it all fits together. You can kind of draw a line right here, and the higher up it is, the more the oxide is favored. The lower down it is, the more the sulfide is favored. And you see things like copper have the sulfide, and this is talking about the precipitate being favored. It's going to be more precipitated out when you have a lot of sulfur. For that reason, as the world oxidizes, you get more of the sulfide-favored elements. But one of the things R.J.P. Williams did is he did things like oxide favored. He's talking about the solid when we're actually supposed to be talking about the liquid if we care about life. And so that's why R.J.P. Williams, that gave me an opening to write about him, So you see that you have these things, magnesium, calcium, manganese. Those were on the red circle on the other one. This is a graph gone using heats of formation rather than KSPs, but it's saying the same thing. Williams was able to put it all together. So we have the different circles that were different parts of natural history. Oh, and right here, iron. It's right in the middle. So that means that iron's going to be kind of special, and it's going to be changing. And the question is, we should look at it closely to see what it is doing. This is a table that does the same kind of thing. Again, we're using enthalpies. This is heat of formation of the oxide and the sulfide. And he calls the hydroxide a version of the oxide, by the way, so don't get thrown by that. And if you look at this, he uses this to explain something that happens in chapter 3. In chapter 3, it says that oxygen bound up all of the carbon and silicon, and it bound up carbon and silicon and aluminum, leaving the iron, leaving the sulfur iron and all of that up to be bound to like the iron and the copper and things like that. So why was I able to say that with such confidence? Because he looked at the difference in heats of formation, and you have a much more negative heat of formation for the oxide for these very prevalent elements. So these are going to snap up all the oxygen first, and it's going to leave, you see that you have these lesser differences. All the oxygen is going to be taken up by these large negative numbers, and that's going to leave these guys, if there was any oxygen left for them, they'd be happy to take it, but they only have sulfur left. And so it's still stable. You know, it's still a negative anion that goes with the positive cation and makes a nice crystal, right? It just doesn't make as much more stable of a crystal than the oxygen does. This is why the oxygen gets locked up in the rocks and is not available for life, because it binds these prevalent elements so tightly. And this is the problem. In a sense, life has to unlock it from these bonds before it can actually use it. So that is a good example of the periodic table relating to natural history. And I want to give you one example. I want to make sure we talk about enthalpy and entropy as well. And so remember that these four parameters are related. And I want to give you a biochemistry example just of metal binding. So this is going to be like the sulfide formation that we talked about, but it's going to be involving lead versus zinc binding sulfur in a sulfur protein. It also relates to chapter 1 and 2. We talk about the sulfur cleanup proteins that go around and they stick to the metals in the cell. Those are called metallothioneins, and this is what one of them looks like. There's not much to this protein. It's basically just an amino acid chain with a ton of yellow sulfurs. And so those are methionines and cysteines that will bind anything. You know, they have negative charge, they're polarizable, they'll form sulfides basically. It's just a protein sulfide rather than a rock sulfide. And so in the brain, this is really important to keep your heavy metal concentrations in the right range. You have metallothioneins inside the cell, and it's one of the reasons why, you know, the whole Irving Williams series being reflected in life, the whole thing about these concentrations are kept low because zinc is sticky. The way the cell does that is it has a sacrificial sticky protein that it sends in to stick to all of the zinc, and lead is even stickier than zinc. And so we can look at this from a thermodynamic standpoint, and we can figure out something about what's going on, not just with stickiness, but with flexibility and moving around and entropy too. So I want to ask you, look at this. These are related, as you would expect. You should be able to take the K and turn it into a delta G very straightforwardly. This is at 298K. And so presumably they did their calculations right for that. But then they measured the Ks at different temperature values. And from that, they came up with a delta H and a T delta S. So the other thing that's sort of complex here is that you have a first, second, and third population. Notice here that you can have up to 4 metals binding. It turns out that just like with hemoglobin, binding one will change the binding of the next one. But it's not an allosteric kind of binding increase like with hemoglobin. This is just sort of a normal, well, the protein's already full, so you actually bind less as you add more. So because there's no structural change with the protein, you end up filling up the protein and having weaker binding sites that come on later, rather than more tight binding sites like you do with hemoglobin. And that's what this looks like. Actually, if you look at the Ks, these are the Ks and the delta Gs. These are delta Gs for binding. Binding is spontaneous in all cases, but you actually have less binding. It's the opposite situation from hemoglobin. Okay? But now you can look at this, and because it's not an allosteric fancy protein, you can actually draw some conclusions about lead and zinc binding. So first of all, let me just ask you the first order question. If you had to say, let's say you had a test question, and you had to say which one of these binds more tightly. Does lead or zinc bind more tightly? Compare each event, and I think you'll see a consistent pattern. Compare each delta G, which is, and you had to put money down on this, okay? So, or at least your reputation for getting things right in class. Anybody want to say which one binds more tightly? Which one is stickier, lead or zinc? Okay, you win the money. So the social reputation of being the right answer in the physical chemistry class. Okay, and that goes along with R.J.P. Williams. Lead is very sticky, you know, and it's especially sticky, and it's one of the things metallothioneins are good for. But then you look at the delta H and the T delta S. And by the way, here's the S over here, but of course, this is units. The T delta S is units of kcal per mole. Delta S is in weird entropy units. So if you really want to compare and say which one has the bigger contribution, you're better off looking at the T delta S, and they made it negative. Let me bounce that off you. Why would you want to compare delta H to negative T delta S rather than just plain T delta S? Yeah, there's a negative in the formula. And so now you can compare these exactly. And the way that it's compared right now, which is better? Which is a bigger contribution of that form of binding energy? Negative or positive? It's like delta G. So chemists think like delta G, and it also goes with the normal way of talking about delta H. So you make this negative. The entropy of the universe is increasing when you have a negative number here, and so that's going to go more. Okay, so I want to ask you, though, this is a binding event. You have two things coming together and forming bonds. Bonds give off heat energy. So you expect there to be a negative delta H when you form a bond, if that's all you're doing. You see some negative delta H's up there, but you actually don't always see a negative delta H. You actually have large positive delta H for the zinc. And then you have a negative T delta S. So from that, what is really driving binding here? What's making binding happen? Is it enthalpy of the system driving it, or is it the entropy of the system? Well, how in the world can we do that? Okay, well, explain that to me. Entropy of the system. How can we have a binding event, which by definition is two things coming together and forming a bond? How in the world are we having the entropy of the system increasing and driving that interaction? There's actually multiple possibilities. So life is weird, but we need to be more specific than life is weird. Okay. That's the thing when I'm grading like a test and I ask something and you're clearly just putting down something very vague and hoping to get some points for it, and I have to decide how much does this show. What could be an entropy increasing process in the process of lead binding to a protein, metallothionein protein, and look at the protein. So the negative entropy means that somehow the entropy is increasing in the system, okay, which means that I should turn it around, because you don't necessarily have heat increase. You necessarily have entropy increasing somewhere. Well, the number of molecules in the system includes water, so if the number of entropy-rich waters increases, then you can have an entropy increase. Jeffrey?
You talked about conformation change, but a conformation change possibly increase the entropy.
Yes, but the question is of what? Because the protein itself is probably more wiggly, and then it bonds, and it's less wiggly. Fewer conformations, less spread out, entropy decreasing. So it's not the protein. But it's not just about the protein. There's other molecules, right? And other water molecules, right? There also could be another part of the protein, like maybe this part actually starts out less wiggly and gets wigglier. There's a possibility that some other part of the protein, and there are proteins where this happens. So you could have more conformations for water, more conformations for the non-binding parts of the protein. You could have burial of hydrophobic surface, which would cause more water release. I think that covers the bases. If
Is that water like defined as segments?
doesn't have to be. It could be somewhere else, but it's easiest for us to think of it that way. You know, at this point, we don't really know where these waters would be, but we could say that it could be water next to a hydrophobic surface, or if a water interacted better with the cysteine, like it formed a really tight bond to the cysteine, then here comes in this lead and pushes it out away, and now it's over here. So its delta H has actually gotten worse, but its freedom has gotten more, and so you have an entropy increase. The main thing here is a lot of biological thermodynamics has to do with entropy increase, even when you have an entropy decreasing main event that you're looking at. What you're looking at is not the whole system. Okay? Now the thing I won't tell you, I have to leave something for the test. The thing I won't tell you is what do you think about the first event, second event, third event? Could that tell you something about how either of these factors, especially like, think of the conformation of the protein going from wiggly to less wiggly, losing entropy. What does this tell you about that possible contribution to the whole picture? And so for that, you have to compare first, second to third. Okay, but I've said too much already. All right? So, yes, Angelina. Okay. Okay, I always will take a question. Okay, yeah. Mm-hmm.
So if you're talking about the entropy of the system, like it was like more water and that's why the entropy is increasing, then like why would the entropy increase with each binding event as more water is released? Or like,
Well, maybe most of the water is released with the first event, and then the second events, the water is already released, and so there's no more left to release. I think that's the way I'd put it. And yeah, take notes. Yeah. But you can compare, if you can think of it that way. This is a nice situation because the protein's exactly the same. The ions are essentially the same, and yet you have a big difference in thermodynamics. Realize that when you get to the third event starts looking normal, because at least there you have some negative enthalpy. So that looks like you have less of the weird stuff going on and more of the expected stuff going on. Okay. All right. So actually, I'm going to do a quick make sure things